Before we begin, though, I just want to acknowledge the traditional owners on the land upon which we're meeting and broadcasting from. I'm here in Western Sydney, and I pay my respects to elders past, present, and emerging of the Darug people. So this is a very special occasion for us. We are recording this because I think it has probably some historical significance, right? We all know of the amazing work of the ocean discovery programs and the JOIDES resolution, right? Many decades of work in exploration and drilling. And as we know, it's also being decommissioned this year without really a replacement platform in place. So that's quite interesting historical. This is one of the last voyages of the JOIDES resolution. So we're very fortunate to have Professor Simon George from Macquarie University, actually beaming in directly from the Mediterranean. We'll get Simon in a moment to talk about the scientific goals. He'll give us a tour of the vessel, and then we can have a discussion and questions and so on. Most of you would know Simon. Simon's a professor at Macquarie Uni, expert in geochemistry, organic geochemistry, with more than 35 years of experience. So I'm really curious and excited to hear from Simon. So let's hand over to Simon. I'm going to ask him to unmute and pin and spotlight and take it away, Simon. Thanks so much for doing this for us.
Okay, cool. Thanks so much for the introduction, Sabid, and welcome everybody to the JOIDES resolution. We are here on the Mediterranean Sea. We're just inside the Strait of Gibraltar, and we have been doing some drilling at this site, our fourth site, and I will be showing you around, telling you a bit about the project, and introducing you to some of my fellow scientists on board, showing you the sort of job they're doing. And then at the end, there'll be plenty of time for Q&A. Before I start the tour, I'd like to introduce Kellen, and I'll just come around the other side so we can be together. So Kellen is one of the outreach officers. Do you want to just quickly introduce yourself as well?
Sure, yeah. I'm one of the outreach officers. I actually work the opposite shift of Simon. So I work midnight to midday, and I'm a medical illustrator. So that's my experience.
Cool.
Yeah.
Thanks, Kellen. So Kellen's going to be holding the camera and will also help answer some of the questions later. So you can see the bow of the ship. What we'll do, we'll walk from this bridge area and we'll walk around to the place where the action happens. Location, you can see the derrick. It's very high stands, about 30 meters of drill pipe at one time. At the moment, we're not drilling. We have just finished logging at this particular hole, and we're going to be moving to a B hole presently. So at the moment, they're probably retrieving some of the gear from the seafloor and getting in preparation for a very small transit to the second hole. You can see there's a lot of infrastructure involved. There's a crane, which is used for moving drill pipe around. There's, of course, lifeboats in case there's an accident, which we walk past. And just over here, when you look down, you can see racks of some drill pipe and some upper pieces of steel, which some of those racks are empty now because it's actually down on the sea floor. So the crew are really experts at putting all the drill pipe together. The capabilities of the ship are amazing. It can drill in more than 5 kilometers of water and can drill more than 2 kilometers below the seafloor. Now, on this expedition, we haven't gone near either of those, but we have been down to about 1.4 kilometers at one of our holes, and we have been drilling the deepest water in about 2.5 kilometers. Okay, so let's go inside and have a bit of a chat about the project. Okay, I think probably if I leave it there. So this is a map of the Mediterranean Sea and the entrance into the Atlantic Ocean over here at about 7 million years ago in the Tortonian, which was a period inside the Miocene. The three drill sites, the primary sites that we have drilled, include these two in black dots off the coast of Portugal. And currently we are here just inside the Gibraltar Strait. We have drilled a fourth hole, which is offshore off this map. That was a repeat of U1385 in a slightly deeper water environment. Now, the context of this expedition is that, as you can see, the entrance into the Mediterranean 6 or 7 million years ago was very different. It was through the north part of Morocco, through the Riffian corridor, and it was through the Betic corridors through the south of Spain, past Granada and Almeria. So we don't actually know if the Gibraltar Strait was open at all these times. It may actually have been closed. So the only way in might have been through here. But in the Tortonian and earlier, the Mediterranean was in connection with the Mediterranean, with the Atlantic Ocean over here. But what happened during the Miocene in the Messinian was that the movement of plates, effectively Africa bumping into Europe, that's the big picture here, meant that these gateways closed. And that meant the Mediterranean became isolated. And because it's isolated, full of salt water, and in a fairly warm climate, there was a lot of evaporation. And we had what's called the Messinian salinity crisis, where hundreds of meters of salt and other minerals were deposited on the floor of much of the Mediterranean. So this was a very major event, which happened between 6.6 and 6 million years ago. At that time, the Miocene ended. We went into the Pliocene, and these corridors were closed, but the Gibraltar Strait opened. And there was a rapid inflow of water from the Atlantic Ocean into the much lower lying basin that was, or is now, the Mediterranean Sea. So there would have been some spectacular waterfalls, probably around about here, and also off the coast of Sicily, where the water broke through. And this water dissolved some of the salt, became very salty. And that led to movement of salty water in and out of this strait. And that is still happening today. There's what we call overflow of the salty water from the Mediterranean. And we know from present day oceanography that it tends to go in the northwest direction, past the coast of Portugal. And we think that's the pattern that water would have been moving from the Mediterranean area in the Pliocene and Miocene as well. So that is why we have drilled these holes in the Atlantic Ocean. We have drilled down to the Messinian in these three locations. We had 2 holes at this one, 2 holes at the repeat hole at the U1385 site over here, and 1 hole in the Gulf of Cadiz. And in all those holes, we've penetrated the Messinian, and we've acquired the core that's going to tell us what was happening in terms of the ocean currents, in terms of the contorite deposits, the turbidite deposits, the normal hemipelagic sedimentation that was going on. And here, this latest site, we're in the Alboran Sea, and here we're investigating what happened in this part of the basin during the Messinian crisis and then subsequently afterwards. And we have some pretty exciting results from there, which I maybe can tell you about a bit later. The last thing I wanted to mention to you is that this IODP expedition is part of a broader project called IMAGE, which is a land-to-sea collaboration between IODP and the ICDP, the International Continental Drilling Program. And with this, in these 2 blue sites in North Morocco and South Spain, we're going to be doing ICDP drilling to recover the sediments that record what happened in these corridors over these periods of movement of water in and out of the Mediterranean, and then eventually blockage. So I'm sure you have lots of questions for me. So please hold off those until slightly later. But now I think we should go for a bit of a walk. I'll show you a bit more about the coring process and what we do in the labs. Okay. Okay, so we're now on the catwalk, which is the area immediately past the drilling floor. So up here is where the drilling actually happens. You can see some of the gear. It's mostly not being used at the moment. They're sorting a few things out after doing the logging. And what happens is the core liners get placed on this yellow pedestal, and these are 10 meters long or so. And in fact, there's some empty ones up here. So these are ready to be deployed for the next bit of coring we do. They go down to the sea floor, go below the sea floor, they get filled with the sediment, and when they're brought up, they come out and are laid out by the drillers, and then the technical staff of IDP, probably about 5 of them each time, or 5 or 6, they carry these cores this way into this catwalk. So the cores get laid up along here. They are broken into 1.5 meter sections, which are then packed with these sorts of plastic cups. And acetone is used to make sure that those are sealed up very carefully. And of course, it's all very carefully measured and labeled so that we know exactly where each piece of core came from. And then it gets taken inside the labs. There's also something called the core catcher, which is the very bottom of the core, which catches and stops the core falling out the bottom. And that contains generally a fairly deformed piece of rock or sediment. And that is extruded on this bench and sometimes with this instrument, used to push out the pieces of sediment from this core catcher. Whilst we're down here, I can also show you some drilling bits. This is a bit just for drilling ahead. It's a normal rotary corer, and you can see it's not got any hole in the middle. So it's just designed for drilling. But these two are coring bits. And what happens is that plastic liner goes through this middle area, or is just behind this middle area, and the rocks go up this hole and into the liner. And these drilling parts are used to then keep on drilling down further into the sediment. So this is the way we actually recover core. Okay. That's all here. Let's go inside. Okay. So the first thing that happens when the core comes on deck is it's put in an area to get it really stabilized in terms of temperature, and then it's wrapped up here. And these are what we call hull rounds. So it's whole core. You can see the identification on it with a barcode. So this is the 78th core, and it's the 3rd section. And that's going to be cut in half presently. But before it's cut in half, there's various physical properties that are done on these whole cores. And that's done in this general area. So these are some of the tracks. And effectively, each section, which is generally about 1.5 meters long, is put on these instruments and then run through these different instruments. This one here is the gamma ray. And that's very useful because the gamma ray response is mainly dictated by the amount of clay minerals. So it's a bit of a proxy for percentage clay, and in reverse, potentially percentage carbonate. Because in these marine sediments, it's often a balance between the amount of clay and the amount of carbonate. I'll just go around the other side. So the physical properties then are used or looked at by physical property specialists. This is you from China. Say just a quick hello to some Australian geologists.
So for this course, we measure the NGR, namely the natural gamma ray radiations, and which can help us to know the contents of thorium, potassium, and uranium in our sediments.
That's brilliant. Thanks very much. Okay, let's go around this direction. So this is the cutting room. After the whole round measurements have been made, and after the, which is generally about 3 or 4 hours, the cores are brought in here, and we have to cut them in half. Now, sometimes we can do that using a wire. So sometimes we have a wire that goes between these 2 devices, so a bit like this, and that's fine for the soft sediments. But of course, as the sediments get more and more lithified, and as they are now, we're going to be using a rock saw, which is in the middle of this device. And soon, this saw will be run along the length of this core, and it splits it into 2. And those 2 halves are then treated separately. They get washed down in the sink area to clean off residue from the cutting process. And then each half is taken out separately. And in this room, we also have a bunch of other rock saws, which I'm sure many of you will be familiar with from geology department rock saw areas. And these are used to cut up the hard rocks into maybe thin section blocks or for other sampling purposes. Morning.
Hello.
I have the Geological Society of Australia with me.
Hello, Geological Society of Australia.
This is Rachel, one of the co-chiefs, and Manuel from Portugal. And this is the description half. So this is the working, this is the working half of the half core. And you can see some of our beautiful Miocene sediments here. And I'll just point out that we can see some silty mudstone, and then some silty sands, and some coarser stuff over here. So this is probably a small turbidite, actually quite a big one. It's all fairly dark greyish green, but it's not always like that. We have had more obvious colour contrasts. And you can see what's happening here. There's a bit of sampling going on. That's probably for a bit of microfossil identification. Just need only a tiny bit for a smear slide. But there's bigger pieces being taken. And this one, for example, is a power sample. So different types of samples get taken in different places for different purposes. Paleomagnetism, PAL, is one of those. And over here, we have 2 of my sedimentology colleagues. This is Natasha and Danielle. This is the Geological Society of Australia, having a bit of a look around. And this is how I spend a lot of my time when I'm doing my shifts. And what we do is we describe onto these hard copy A3 sheets, although we're on a US ship, so it's not actually strictly A3, is it? It's some other funny size. So we make a sedimentological log through each section of each core. And we also then record the information into a computer. So in fact, there's 2 fairly independent but related measurements, descriptions of the core. To help with this, and in fact, before we start the description, we photograph the core. And we do that on this track here. This is a very high resolution camera, which basically takes a very high resolution photograph of each half core. We do that fairly quickly after cutting the cores because the colors can change over time. So it's good to get an immediate record of the colors. Just occasionally we have to do it again a bit later because they dry out and change color. So this is quite an important adjunct to the description that we do, because sometimes there's things that you can see on these high resolution photographs that the describers can't actually see under the sort of lab light that we have here. Now down this way is another. And this one's quite new to the JR. This is an X-ray scanner. And the cool thing about this is we can run the samples on a track into this machine. Open it up for you. So here is the hole into which we push the half cores, and they go away in there. And this enables us to take a photograph of the inside of the cores. So we can see internal structures. And we've actually found this very useful for working on some of the trace fossils, some of which are obvious on the cut surface, but others which are buried beneath the surface. And we find that by adjusting the X-ray images, we can actually get a really nice internal picture of the cores. So we use the high resolution photographs and the X-ray images as we do the describing. This track is the section half multi-sensor logger, otherwise known as the schmizzle. And this enables us to do some more measurements on the half cores. We measure the magnetic susceptibility here. It was previously measured on one of the other instruments, the physical properties on the whole round, but here it is measured on the half round. And also there's another spectrometer which measures the reflectance at different wavelengths, which also gives us information about the properties of the core. Hi there, guys. Sort of Josh from Starting Australia around. These are two of my other colleagues in the STED team. This is Kosuke and Javier. And you can see Kosuke's on a microscope, and he's having a look at some smear slides, I think, probably, which are pictures of the rock. So it's a normal petrographic microscope. So the smear slides can be made very quickly and very easily. It only takes about 20 minutes to make a smear slide from the sediment. But also we can make thin sections. And in fact, last night we got our first batch of 6 thin sections back, which we have just started analyzing. Thanks very much. So this track is where the paleomagnetism on the half cores is measured. So the cores get sent on this track into this machine, and that measures the remnant magnetism that is recorded in different minerals inside the sediment. So that can be very useful for dating the rocks, because we can see the positive and negative reversals, hopefully, if it works well. It doesn't always work well, but the optimism is we can see that, and that will help us dating where we are in the sedimentary record. In my opinion, this is one of the nicest labs on the ship because it's so quiet, and it's also got some of the best views. So it's quite good for looking for birds or whales. But this is the paleo preparation lab. So the core catcher, part of it is kept for the paleo people, and they will use various methods for getting fossils out. A lot of it will involve water and sieving and filtering to get different size fractions, because the forams, for example, might be coarse ones, or they might be quite fine-grained. The nanofossils, which are sometimes the most useful for telling us the age, they are generally analyzed just by a toothpick sample from the working path and put on a smear slide. So a very simple analytical approach for the nanofossils. And then through here, we have the paleontology microscopes. So Zach is one of the paleontologists on board on the night shift. And you can see lots of different microscopes here, all used for a particular purpose, for describing different types of fossils. And in fact, there's also big libraries. So for example, this is a classic reference book. Yeah, that's a benthic forams. So when we find some particular fossils, the paleontologist can work out how old we are. Oh, and here's Zach's got some really good examples here.
Of planktonic foraminifer and also nanos.
Yeah. And what do you mostly work on?
I work on planktonic foraminifer. Yeah. For this, we use this binocular. Big microscopes is for nanos, even smaller.
Sure. Thanks very much, Zach. Okay. So on the walls here, we have lots of previous expedition logos. So there's a lot of history. And I have been wondering what's going to happen to this when IODP is not using the ship anymore. I'm sure they'll be kept, but I don't know where they'll be put. So this is the chemistry lab, which is particularly well equipped. And I'll show you first the history. So we measure the amount of carbonate and the amount of organic carbon. And to do that, we have to better measure the weight of samples. So this is a compensating balance, which means that the rocking of the ship is compensated for by using two sides of the balance. So you can get pretty accurate weights, which are suitable for doing then the elemental analysis, which is on this machine over here. So this measures the carbon, hydrogen, nitrogen, and sulfur, CH&S. And that is one of the ways we can then measure carbonate. So we measure the carbonate on a coulometer. We measure the total inorganic carbon here, and the difference between them, that gives us the total organic carbon. A very important role of the chemistry lab is testing the gases as we drill. And what they do, so I have been in this lab on a previous expedition, but this time I'm sailing as a sedimentologist. But a small sample of the sediment is put into a glass vial like this, and then it's sealed with a stopper, and then it's put in an oven at a steady temperature for half an hour or so. And that means that any methane and ethane and wet gases that are in the sediment get dissolved out into this headspace. And then what happens is a syringe is used to go through the septum and samples a part of this headspace. And then that gas is then introduced into this inlet of a gas chromatograph. And this is specially designed for measuring the different gases. So we can do from C1 to C5 gases on this instrument, and we can do carbon dioxide, which are all three very useful gases to be analyzing. And it's a safety thing because we want to make sure we're not drilling into a gas reservoir. There's a lot of seismic work done before we drill to make sure that's very unlikely. But as a safety precaution, every core, one of these little gas samples is taken and measured by the chemistry team, and it's plotted on a diagram which helps us understand the risk of gas. And in fact, on the last expedition I was on in New Zealand, we had to stop drilling deep in the Paleocene because the amount of methane went too high, and we started getting into a risky area where there could have been a natural gas accumulation, So we had to stop drilling. Okay, so the last thing I want to show you are the presses. So these are big hydraulic presses where rock from the sediment core is brought. We probably don't have any left here, I don't think. But effectively, the residues from them are in here. So we scrape off the sides of the core into this bucket, and then the inside part of the core is placed inside these metal containers. Oh, that's brilliant. Thanks, Johanna. So there we go. A whole round core, which is stabilizing, and it's getting ready for squeezing. So it's amazing that we've still got some samples like this from really very deep. We've been down more than 1,200 meters, and we've still been able to get some of these whole round cores. And then this hydraulic press puts a lot of pressure on, and there's a syringe here, which is then being used to capture the water that's being squeezed out. And that's what's called the interstitial water. And that tells us something about the chemistry of the water in the formation at the present time. So we can understand a lot about what's been going on over the past by understanding the chemistry of the water. And we measure the chemistry of the water using various instruments in this lab, including this instrument. Johanna?
Yeah, I see it's running right now. It measures cations and anions.
Thanks very much, Johanna. Johanna's one of the IODP technical staff. In fact, I sailed with Johanna back in 2009 and 10, so we go back a long way. And over here, there's an ICP, and we use that for doing some of the other elements that we can't do on that instrument. So it's a very well-equipped chemistry lab. We can do an awful lot of things on the ship. Okay. Okay, so that's the tour finished. So I guess I'm now available for 10, 15 minutes or something to answer any of your burning questions.
This one in the chat.
Well, that's amazing, Simon. I'll just start by thanking you. I mean, particularly because you're such an amazing ambassador for Earth Science. I know how closely you work with outreach in Sydney and the rest of Australia. So thank you for your time. That was amazing. I'll open up to questions. And we have one question already in the chat.
Okay, so I see the question from Joe. Do we know how thick the salt was? Did much of it dissolve in the inflowing water? Yeah, so not all of it dissolved. I said hundreds of meters, and it really is that much. It's preserved in parts on the surrounding land now, in a few places, but a lot of the times it's actually below the ocean, below the sea. So it's kind of inaccessible except by drilling. We deliberately avoided finding any salt, so we picked an area within the Mediterranean that we expected not to have salt, and it did not. So that worked out well. But it is hundreds of meters thick, and some of it definitely dissolved when the Mediterranean reflooded. But I would think it's probably fair to say the exact proportion is kind of uncertain. And understanding what happened to that salty water is one of the main expeditions, one of the main aims of this particular expedition.
So just to follow on with that, Simon, are those gypsum deposits that in Cyprus, is that part of the same story?
Yep, they are.
Right, cool. They were very, very impressive.
Sounds amazing.
Yeah.
I've got lots of questions, but I want to open it up to others.
So I see a question from Leanne. Thanks for the question, Leanne. Does ICDP share data with IODP in terms of the drilling site? Yeah, that's a very good question. Yes, we're going to work really closely together. And in fact, Rachel, who you met as one of the co-chiefs, she is also going to be leading the ICDP drilling. So she's the general project leader. And we've actually got a standard IODP moratorium on the samples, but also that's being extended until the ICDP drilling is done, because that's not going to happen for a few years' time yet. And in fact, we still don't have funding for actually those ICDP holes. So in the next 3 to 7 years, I expect that drilling will be done. And yes, we will be sharing information, samples, and we will probably try to analyze the ICDP samples in the same way as we have done so with the IODP samples.
And Simon, just to follow up though, for the rest of us, ICDP is the continental drilling program, right? The onshore partner, or yep.
That's right.
Okay.
Yeah, that's right. It's the continental drilling.
Great. Paul has a question.
Yes. So do we know how long it took for the Mediterranean to refill after the Messinian? That's a really good question, Paul. Thanks for that. I think it was over many, probably hundreds of years. There have been some calculations about how long it would take, and it partly depends how big the waterfall is heading in. I'm a bit uncertain about exactly the age constraints, but it's not an instant thing by any means. It's something that would have gone on for many, probably I think hundreds of years, this refilling of the basin, because by the time the evaporation had happened, the Mediterranean was a long way below base level. So, and it's a huge basin. So it required a lot of water to get through. And we can see the evidence of that in some of the subsea canyoning and stuff off Sicily and off Gibraltar.
Great stuff. Can I jump in with a question? Simon, you started talking about the repeat hole. Why, why do you do the repeat hole at the beginning?
Yeah, right. So U1385 was an interesting one. It's called the Shack site. It's actually been visited twice before by IODP. But every time, and they had drilled up to the J hole. So they drilled A, B, C, D, E, F, G, H, I. That's 10 holes previously, but they'd neglected to go below the Pliocene. Those first 10 holes had all been targeting the Pleistocene and Pliocene record. And it wasn't until quite late on in a fairly recent expedition, was it 397, that they realized that the cyclicity that had been seen in the Pliocene was very likely to be continuing in the Messinian. And they realized, well, we really should have drilled down into the Miocene to recover the Messinian record, but they didn't have time on their expedition. So they contacted Rachel and said, well, seeing as you're drilling up the slope at one of our primary sites, would you be interested in having our area as a secondary site? And we said yes, or Rachel said yes. And then it was about time budgeting, and we were very fortunate that we were able to do a few things quicker than we expected. We've had a really successful expedition in that we drilled two holes at the first primary site, and then a very deep hole in the Gulf of Cadiz. And then we calculated we had time to go back to 1385, and we actually drilled 2 more holes there, both into the Messinian. And the 2 holes are complementary. They are the K and the L holes. And the second hole, the L hole, fills some gaps that we left behind in the K hole. So that is a deep water record of the overflow from the Messinian. And now we're in the Mediterranean, and we've just completed this A hole, and we're shortly going to start a quick B hole to finish off the expedition.
Amazing. There's a question now from Leanne.
Yeah, so the refill history, Leanne, that's a very good question, and it's something that would be really good to know more about. There's some famous pictures or artists' impressions of what it would have been like. Undoubtedly, the width of the opening would have been very important to control exactly where it happened. And also, it probably didn't happen just in one place. As I say, there was constriction around Sicily, and that would also have opened at some stage, and water would have flowed through into the eastern part of the Mediterranean. So the western and the eastern Mediterranean might have refilled at somewhat different times. And in short, this would have been controlled by paleogeography about the movement of blocks and eventually a breakthrough. So what would have been low-lying land, maybe there would have been a storm surge or something like that. Sea level rose a little bit, and that started the process that the water could actually move through. But it would have been an amazing phenomena to see, and there's nothing around today that tells us what it would have been like. There's nothing in human history of so much water flow over such a long period. It would have been a spectacular thing.
I've got one more question, if I may. Have you seen anything apart from sediments? I know you're the sedimentologist on board, but have you seen any volcanic rocks?
Yes, Joe, we have.
Yes.
But not very many.
Well, I did do my honours on Miocene volcanics in southeast Spain, so you know I'm kind of interested.
Yeah, right. So yes, we have in class of some of our sediments. So we have recovered conglomerates, and also some of the sandstones in the turbidites contain items that we think are related to some of these provenance of volcanics, and also some metamorphic rock fragments. So we have seen some volcanics like that, but also to the east of where we are now, there's thought to have been a volcanic chain that joined Morocco and Spain in the Miocene. And we're especially looking out for volcanic shards in our smear slides. And I've actually discovered quite a few. One of the co-chief that you didn't meet, Manu, she's very interested in that. And she's trained some of the sedimentologists to look for these little volcanic rock shards. They're tiny, 10 microns across. And I found quite a few. So I label the samples where I find them, because Manu and her students will go back to these and try to recover some of them and do some chemistry on them to work out the evolution of those volcanics. And the idea is it may have changed from an acidic type thing to a mafic type thing over time.
Yeah. Fantastic. Thank you.
Hey, Simon, I know that we're probably running out of time, but I think a really important question is August is the decommissioning, right? What happens after August? You know, we've got 71% of the Earth's surface, you know, ocean, and then really what 90% of that then becomes inaccessible to, you know, ocean, seafloor drilling and so on. What does this all look like beyond August? Can any of the commercial ships do this? What's the future of all of this?
It's a multi-dollar question, Sabine. It's very good. Well, what's immediately going to happen after August is the IODP is going to take all its gear off this ship. So all these instruments I've shown you are going to be kept at Texas A&M. So they're going to be available for future work. So that's the first thing to say. And this ship itself will probably go on to a different owner or a different client for use somewhere else. So in terms of how we as scientists then access this rock record, is a really tricky question. We still do have a couple of drilling ships. So we have the Chiku in Japan, and we have the new Chinese ship, which is being commissioned soon. But probably, well, we know the Chiku doesn't venture far from Japan, and it's very expensive to run, so it's got several disadvantages. And we suspect the Chinese ship will be mainly used in Chinese waters, although that's, I guess, not confirmed yet. So you're right, there's a lot of the world's oceans which will become inaccessible to geologists. Potentially, we could run through the ECORD model, where we look at mission-specific type platforms for doing ocean exploration. And I see no reason that current ECORD thing will change. So that's where we hire a particular vessel that's suitable for the needs. Now, in the past and up to now, we haven't needed to do that for main ocean exploration because we've had the JR. But in the era where we won't have the JR, potentially IODP could hire a ship to do to do research. But this is very much still in exploration. We don't know how this is going to work, and it's important because even if the USA decided to spend money on a new ship, it's not going to be here for, it's got to be at least 10 years. So there's going to be this huge gap in the ability to explore the world's oceans, and it's a real tragedy that it's happened. Very, very sad. But as I say, there are potentially ways we could have fixes with using some half-or vessels, which might fill some of the gap.
Thanks, Simon. Do you know of any of the heritage kind of preservation works to, preserve this, some of this, for future generations? But you're saying that a lot of this will get repurposed for other work.
Well, the ship will be, for sure. As I say, the instruments will be kept, and potentially they could then be deployed maybe in a sort of containerized way onto other platforms. So that can still work. But the other important thing to say is the outcome of DSTP and ODP and IODP is a load of samples in core stores and a load of data. And that's all going to continue to be accessible and to be used. So just as many of us have accessed IODP collections to get extra samples, we'll still be able to do that. The big core repositories at Texas A&M and Bremen and in Japan will still be open. So there's been a lot of drilling done in the last 50, 60 years, and we can still access those cores. And for example, the cores that we've acquired on this expedition, we've been talking a bit about this, and we expect that geologists will be working on the material that we've collected in this expedition for many decades, probably 40, 50 years. In 40, 50 years' time, geologists will still be coming back to U1611 and trying to sample it for the newest analytical idea, technique or new research idea, because what we've acquired in this expedition is so unique and kind of so important. So the samples, not just from this expedition, of course, but from all these hundreds of other expeditions, do provide a very much an ongoing, very valuable resource for geologists in the future.
Yeah, that's a very important point. Any other questions from the team, from the floor? I have one last quick one. It looks like that we've run out of questions, but I have one last quick one, right? These voyages are known for the very good food on board. Tell us what you've been having in the Mediterranean. School kids might be interested what day-to-day life might be like.
Yeah, I didn't go so much into that compared with, say, talking to the 10-year-olds. But, well, I tend to have a normal breakfast by myself, just a bowl of cereal. But the food is very varied. Just because we're in the Mediterranean doesn't mean to say we have a Mediterranean diet, of course, because the ship's food has been all taken on in Amsterdam and we're still lasting off that. But we still have oranges and apples and pears. There's a good variety of dishes served every day. I don't think there's quite enough vegan food personally, but maybe a bit too much deep fried fatty food for my liking, but there's always other options. And I actually rather like the Filipino dishes that always get served. How about you, Kelly?
I'm a vegetarian, so I've been eating a lot of eggs. It's a lot of, that's most of what the vegetarian option is eggs. So, but they have a lot of really unique meat options. We had rabbit for Burns night.
And haggis.
And haggis, of course. But there's also usually fish and beef and pork. So you do not go hungry, that's for sure.
Yep.
Great. That's amazing. Well, what a way for us to start the year with our GSA meetings. This is recorded and hopefully it'll be a great resource for the future. So Kellen, thank you so much for organizing this and for all your hard work. Simon, thank you so much for taking us around and talking about the science and life on board. And yeah, truly a historic moment. So thank you both.
Thank you.
Thank you. Thanks for
Thanks,
organising.
guys.
All the best,
Thanks.
everybody.
Good to see you.
Goodbye.